Hi, I am Sherwin Dave Suwako, a second year Bachelor of Science and Electrical Engineering student. This time, we're going to solve and I'm going to explain how to get the value and the answers of the various problems regarding the allowable design stress and also the thin-walled pressure vessel. And now our problem number one is if each of the three nails shown in the figure below has a diameter of 4 mm and can withstand an average shear stress of 60 megapascal, determine the maximum allowance for speed that can be applied to the load. So we have here given, which is diameter 4 mm and the allowable shear stress, which is 60 megapascal. And if you write the FBD of the problem, so you notice that the applied load is distributed evenly to the three rivets. So it is called also a shear stress, or it is the three lines is tangent or it is parallel with your cross sections. And we can write from the formula 3. We have here a 3V, which is your the V is your tangent line with respect to your cross section. So it is 3 equals P. And by derivations, you can derive the formula by V equals to P over T. You can use that later. And the second one is find your cross sectional area. And to find your cross sectional area, you have your formula A equals pi over 4 multiply by your d squared. And you can substitute the value pi over 4 and you have your value of your diameter here, which is you can convert the value of your 4, which is 4 millimeters, convert it into meter, so therefore it will become 0.004 meter. So you can substitute the value in meter, 0.004 squared, and you have now your value of your A, which is 4 times 10 raised to negative 6 pi meter squared, or there's also 1.2566 times 10 negative 5. And now you already solved your area for your problem, and now let's move on to answer the question of your problem, which is to determine the maximum allowance force P that can be applied to the load. So you have your formula here, which is allowable equals to V over A. So V over A, then you can substitute the value or the value of your given formula, which is the allowable shear stress that can be applied is already given, which is it is 60 megapascal. So you can write the value here, 60 megapascal. So it is in mega, so therefore you can write it 60 times 10 raised to 6 equals to V. What is the value of V? So the V is equals to P over 3 from the derivations of your 3 rivets that is distributed evenly to your cross section. So therefore your value V is P over 3 multiplied by your area, which is here 4 times 10 raised to negative 6 pi meter squared. So therefore by manipulating this, you can solve, you can multiply the 60 times 10 raised to 6 by 4 times 10 raised to negative 6 pi, and then divided it by 3. So therefore you can solve the P, which is 2.261 kilo Newton. So therefore the 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 maximum allowance for speed that can be applied to the load is 2.261 kilo Newton. And now our second problem is if the eye bolt is made of a material having a yield stress of 250 megapascal, determine the minimum required diameter of its shank. Apply a factor of safety, which is 1.5 against yielding. So you have now your free body diagram here, and our given is we have the factor of safety, which is 1.5, the P, which is the load, which is 30,000 Newton, and the stress, which is 250 megapascal. With the formula of the factor of safety, we can write as F of S equals to 1.5 equals your load failure here is 250 megapascal, so you can write 250 megapascal, and your allowable load here is not given. So let us say that it is this, and the 1.5 here is the value of your fs that is already given by your problem. So we can compute the allowable stress by 250 divided by 1.5. So it is become 166.67 megapascal. So you have now your allowable stress, but the required is to find the minimum required diameter of the shank by applying the factor of safety. Note that the normal stress is occurring because you are pulling on the eye bolt. The direction of the load is perpendicular to the cross-sectional area. Okay, and ito siya. And we can write the allowable formula here again, which is allowable equals to P, which is your load, and your A here. So to find P, so it is already given, which is 30 kilonewton, or it is 30,000 in Newton. 30,000 Newton over your A, which is your A here would be pi over D over 4 D squared, which is this formula is in the circular area. So therefore, by computing this, so your allowable stress here is given. So therefore, we can write this 166.67 megapascal equals 30,000 Newton over pi 4 d squared. So we need to find the required diameter by manipulating these equations. So by manipulating these equations, we can say that we put this in the left side. So therefore, we can it is become 30,000 Newton over pi d squared, and this 30,000 you multiply it by 4. So you multiply it by 4 and then over pi d squared, and then equals to 166.67 megapascal. And you can solve now your d here, which is by manipulating. So d equals to square root of 30,000 divided by 166.67 multiplied by your pi. So you have now your d here, which is 15.1386 millimeter. So the required diameter of its shank that applying the factor of safety 1.5 against yielding is 15.1386 millimeter. That was the answer of our problem number 2. Our third problem is if the bolt and the supporting bracket shown in the figure are made of the same materials, having a failure shear stress of 120 megapascal, determine the maximum allowable force that can be applied to the bolt so that it goes not pulled to the plate. Apply factor of safety to 2.5 against the shear failure. And you have your FBD here, which is you have your P. So your P here is your reaction force. So this is your reaction. Your P here is your allowable force, rather. It is allowable force. And your V here is your reaction force, which is parallel with the cross-section. And from a given FBD, we can say that this is the shear plane for the bolt, and this is the shear plane for the plate, and you have your diameter here that is given. So from a given problem, you have your failure stress here, which is 120 megapascal, your factor of safety, which is 2.5, and your diameter of your plate, which is the diameter of your plate is 0.08 meters. The diameter of your bolt is it is 0.04. The thickness of your plate here is 0.03 meters, and the thickness of your bolt here is 0.05 meters from your given FBD. And now we can find the allowable shear stress by substituting the formula by allowable So allowable equals fail stress factor of safety, which is we can substitute the value. This is your fail here. This is 120 megapascal, and your factor of safety is 2.5. You have now your allowable stress shear stress, which is 48 megapascal, and that we can use it later if we solve the value. And now we can also find the area of the shear plane for plate. So area for shear plane for plate. So let us say that is area of the plate, which is equals your pi here, the diameter of your plate. Or let us say that it is P, and the thickness of your plate. Okay, and substitute pi. The diameter of your plate here is 0.08, and the thickness of your plate here is 0.03. So and the area of your plate here is 7.54 times 10 raised to negative 3 meters squared. So that was the area of your shear plane for plate, and we can also solve the area for the area of the shear plane for our bolt. So let us say this area for bolt. So A, let us say that this is the A bolt equals pi, the area, the diameter, which is diameter B, which is your bolt, the thickness B. Then substitute the value of your diameter of your bolt is 0.04. So it is 0.04, and the thickness of your bolt here is 0.075. And you have now your value of your bolt here is equals to bolt here is 9.43 times 10 raised to negative 3 meter squared. Now you have now your area of your plate and the bolt, and we're going to solve the questions. So to find the allowable load, the question is determine the maximum allowable force, and we have now your allowable stress here. So, and you have already your area of your plate and volt. So to find out the allowable load, consider the smaller area of both bolt and plate. Allowable area equal to the area of your shear plane for the plate. So the allowable area mo, this is your allowable area. So it is equal to the area of your shear per plate. So it is equal. So A, the area of your allowable is equal to the area of your shear plane per plate. So therefore it is 7.74 times 10 raised to negative 3 meter squared. And then to find the allowable, we can use the formula allow equals to P over A. Lagi na lang po natin itong ginagamit yung formula na to. And we can now solve the question, which is your given here is your allowable shear stress is 48 megapascal. And your P here is what we're going to find. Your A here is equal for the shear plate for the plane. So therefore is 7.54 times 10 raised to negative 3 meters squared. And then by calculating it, so we can solve the value of your P, which is 361.92 times 10 raised to 3 Newton, or 361.92 kilonewton. And then you have now your allowable force that can be applied to the bolt so that it goes not pull through the plate. The solution. Number 3. The fourth question is determine the required diameter of the pin at A and B to the nearest 1/16 in inches. If the allowable shear stress for the material is 6 psi, pin A is subjected to double shear, whereas pin B is subjected to single shear. So let us say that pin A, it is subjected to double shear, and B is for the single shear. And first thing first that we need to do is to solve the reactions, because at pin A, you have your two reactions here that is don't have any value, and your dy here is also don't have, and the only value that you have is your applied load here, which is your C, which is 3 kips. And then you can solve your equilibrium equations. So equilibrium equations, we need to some moment at A, because it is more than it is have many more than one to value that is unknown. So you have your summation of your moment at A equals to 0. So moment at A, so your sign convention is going to clockwise. So at your A, you have your 3 kips here. So if we move it going to the right, so therefore it is going to your sign convention. So therefore it is positive, and then you can write your the perpendicular distance, which is 8 feet. So multiply it to it. Then what are the other forces? Which you have your dy here. It is going to upward. So therefore, if you move it going to the upward, it is opposed to your sign convention, which is your clockwise. So therefore, it is negative dy. And then what is your perpendicular distance with respect to your A? It is 12. 6 plus 6. So 12 equals to 0. So therefore, the value of your dy here is negative 2. Negative 2 kips. Or dy is positive keeps going upward. And then you have now your value of dy here, and then you can also sum the moment along horizontal. So f of x equals to 0. So what are the horizontal forces? You have your ax going to the right, so it is positive, and your 3 kips here, this plus 3 kips going to the right also. So therefore your ax here is negative 3 kips, or it is also ax equals to 3 kips going to the left. And then we can also sum the moment along vertical. So by forces on vertical, let's solve summation along vertical, f of y equals to 0. So what are the forces? So positive ay going to upward, and then plus 2, which is the dy that is already given, 2 kips. So therefore ay mo is negative 2 kips, or ay mo is 2 kips going downward. So to find the resultant force, we need to calculate the value of your the summation of your ax here and ay. So at resultant force here, so fa, your resultant here, this is your resultant. So fa equals to ax squared plus ay squared. So therefore f of a is 3 squared plus 2 squared. So f of a equals to 3.606 kips, or 3606 lb. Okay, and then you have now your resultant force here. So let's move on to the pin. The FBD of the pin A is subjected to double shear. A is subjected to double shear. So let us say pin A that is subjected to double shear. So FBD at pin A. At pin A, it is double shear. So therefore, it is something like this. So, yan. This tapos let's have a normal force here, FA, and you notice that it's double shear, so therefore the value of your FA will be divided into 2. So let's say over 2, FA over 2, and then the formula is the shear stress. So it is double shear, so therefore FA divided by 2, then the area, which is pi over 4 d squared. Area equals to f of a divided by 2 is your 3 3.606 divided by 2, it will become, so 306 divided by 2, and then pi 4. What is the diameter? So the diameter here, you can manipulate the equations here, because the question is you need to find the required diameter here. So therefore, by manipulating this, so you can have now your diameter here, which is 6,000 lb inches squared, or the diameter of your A would be 0.6186 inches, or to the nearest, the question is to the nearest 1 over 16th. So therefore, the nearest 1 over 16th, it is your DA here is 5 over 8 inches. Because 5 over 8 inches is 0.625, that is also the same with 1 over 16. So this is the required diameter of your pin at A, 5 over 8 inches. So let us move on to the required diameter at pin B, which is single share. Let's move to the required diameter for the pin at D, that is in the single share. And you have your FBD here, which is, this is your D, and you notice that there is a slope. So first, to get the value of your FAC, which is this your FAC, which is this. To get the value of that, we need to find, we need to moment at D. So moment at D, it is in the slant position, so therefore, you need to work for your slope. So you can solve for your moment at D. So you my perpendicular distance is only the x, so it's only the x, so therefore 8 divided by 6 10 FAC, and then your 8 here would be your perpendicular distance, then plus 3 multiplied by your 8. Okay, the 3 is the value of your dy, the 3 is the value of your ax rather. Okay, then you have now your FAC here is equals to 0. FAC here will become 5 kips. Okay, and then you can now solve the value of your required diameter. V over A equals to 500 lb divided by 4 over 4 dB squared. And you can manipulate the certain equations, so you can have now your value over D equals dB equals to 1.03 inches. So your dB here, nearest to 1/6 is dB equals to 1 over 6. So that is the answers, the required diameter at point B. This point B. Okay. Our seventh example is air pressure in the cylinder increased by exerting forces 2 kilonewton on the two piston, each having a radius of 45 millimeter. If the cylinder has a wall thickness of 2 millimeter, determine the stress in the wall of the cylinder. So we have here given, just we have a thickness here, our pressure, air pressure that is inserted, and our radius. So first, we need to find the internal pressure here. So let us say that it is in the italic form of P, and your P here over A. So your P here is 2 times 10 raised to 3 Newton, and then your area here would be pi multiplied by your radius, which is 0.045 squared. So the answer is 3143 80.345 PA. Okay, then after that, we substitute to calculate the stress in the wall of the cylinder. So this is stress PRT. So by substitute, the value of your P here is 380 divided by 1345 Pascal, and then you multiply by your R. What is your R here? So it is 0.045, and your thickness here would be 0.002. So by calculating the amount, so you have now your stress in the wall of the cylinder, that is 7.07 megapascal. 7.07 megapascal. So that was your stress in the wall of the cylinder. And our last problem, the A36 steel band shown below in 2 inches wide and is secured around the smooth rigid cylinder. If the bolts are tightened so that the tension in them is 400 pounds, determine the normal stress in the band and the pressure on the cylinder. And we have here an FBD. So let us see, this is the cylinder. The given is, we have the internal pressure, we have a 400 lb, the radius, which is 8, and the thickness, which is 1/8. So A, we need to calculate the normal stress. So normal stress, let us say that is a normal stress. Okay, and then the formula is P over 2T equals to, your P here is 400, 2 multiplied by your thickness 1/8. So the value is 16 psi, 1600 psi. So that was your normal stress. Letter B. Calculate the pressure on the cylinder. So calculate the pressure on cylinder. So Q equals to PR over T. So your stress here would be 1600, that is from your now you're given, which is your normal stress here, 1600 divided by your P here, which is the unknown, and then you multiply by your R, which is your R here is 8, your radius divided by your thickness 1/8. So by simplifying it, 1600 you multiply by 1/8. So 1600 multiplied by 1/8, and then divided by 8 to get your P. And then by calculating it, your P here is 25 psi. So therefore, the normal stress of is 1600 psi, and the pressure inserted into the cylinder is 25 psi. So that was the solution of the problem number 8.